Well, good afternoon, everyone. I hope you've all had a great lunch. Your speaker for this afternoon, first cab off the rank, Anna Herlihy.
All right, can you hear me? Awesome. So, hello, everyone. My name is Anna. I work for MongoDB in Stockholm, Sweden. The first thing I want to do is to thank the LinuxConf organizers for having me. I'm super psyched to be in Australia, super psyched to be at this conference. I think Gold Coast is the greatest, so thank you. What I'm going to be talking about is a project called BSON Transpilers. So what it is effectively a meta transpiler. So this is going to be a pretty technical talk, but it's great that there are not so many of us, so if something doesn't make sense, if I go too fast, if you just need a breather, just let me know. I am more than happy to explain. That being said, I do have a lot of stuff to get through, and everything I say to you is documented online in lots of detail. So if something flashes by and you want to know more about it, I'm sure there's definitely going to be more information available online. So my goal for this talk is to hopefully inspire you to contribute to this project directly. But if contributing is not your thing, then I would at least say I'm super excited to talk about a project that is really cool and was also developed in a relatively unique way. So first thing I'm going to do is I'm going to talk about the feature requirements that led me to work on this project. So from a MongoDB user's perspective, what needed to happen. I'm then going to take those feature requirements and refine them into technical requirements that as an engineer I can actually solve. And then lastly, I'll go through how you can contribute and how the whole thing works. So first thing, how many people in this room have used MongoDB before? Great. How many people have used Compass before? All right. So MongoDB Compass is basically the UI for MongoDB. So you can do administrative tasks, you can sort of check your cluster health, you can make new indexes, you can sort of do almost everything you'd like to do as a database administrator via a user interface. So you can read your data, you can write aggregations, you can write queries, that kind of thing. So the feature I want to talk about specifically within Compass is two-part. The first part is called export to language. So something to know about MongoDB products is that generally when you write queries and aggregations, you'd write them in MQL, which is the MongoDB query language, also known as MQL, like SQL. So when you use the shell, for example, you would write using this shell syntax. And the shell syntax is a JavaScript-based syntax. So we have this user interface, and you can visually build aggregations, and it generates shell syntax. But the thing is that as a developer, you write programs in programming languages. So you write in Python, in Java. Say, out of curiosity, what languages do people generally use here? Rust. Python. C++. Cool. Awesome. So all of those languages are MongoDB-friendly languages. And say you want to build your aggregation and then export it into something you can use in C++, you can then copy that aggregation into your application directly. And this is great because aggregations can get pretty long and pretty complicated. So that's one feature. The other feature is, this is what it would look like with an aggregation. This is what it would look like for a query. So that's just to give you an idea of what that feature actually looks like when you're using the application. So that's also used on MongoDB Atlas, which is database as a service. So those are all, this export functionality is available on all these different websites. But right now you build in shell syntax and then export into programming language. Wouldn't it be better if you could just write directly in the programming language that you want to write in? So instead of writing everything from number types to string formats, that kind of thing, right now you do it in JavaScript. Wouldn't it be great if you could just do it in C++ directly into the app? And so what that feature is called is language modes. So we want to be able to provide the ability for you to tell Compass, hey, I want to enter Python mode. All my examples are now in Python. All of the input forms now accept Python syntax. And the query that is, or the aggregation that is generated is in Python. So just to take a step back, I want to talk a little bit about the words that I'm using. So MQL is the MongoDB query language, also known as BSON, which is binary JSON. So the thing to know about that is just that it's basically JSON with some extra types. When writing queries, you're writing it in MQL, but you're also generally writing MQL in a given programming language. And so when you write MQL in a given programming language, you actually use a pretty big percentage of the programming language. So you're not necessarily using, say in Python, class definitions or decorators, sort of higher ordered language features, but you are using stuff like literals, data types like arrays, dictionaries, that kind of thing. But when we want to approach the problem of translating MQL between programming languages, we want to, at least at the beginning, treat it like we're translating the entire language. That also leaves the door open if we want to go on and take this transpiler and go full language to full language and not even be MongoDB specific. So what does that get us? We have our two feature requirements. We want to accept queries and aggregations in any language. We also want to generate queries and aggregations in any language. So what that really gives us is any language to any language translation. So this is what I mean when I say transpile anything to everything. We should be able to allow you to translate from JavaScript to Python, also from JavaScript to C#, also from Python to C#. So we end up with this anything to anything translation that we need to support. So how do we actually go about solving this problem? So say these are the 4 languages we want to start with. The naive approach would be obviously to write a translator from A to B. So generally when I say transpiler, it's the same thing as a compiler, just generally when you're talking about transpilers, it means going from user-written language to user-written language. However, compilers are from user-written language to machine code, as I'm sure a lot of you already know. But they're basically interchangeable because the technology behind them is pretty much the same. So this is the naive approach. We don't really want to write that many transpilers. That seems like a lot of work, also unsustainable. So what do other people do to solve this problem? So we could use something called an intermediate representation. If anyone has used Clang or is familiar with LLVM, that's what they use to solve this exact same problem. So what they do is they take an intermediate language syntax, translate into that language syntax, and then translate again in a separate step out to the target language. So we can call our input language our source, and we can call our output language our target. So this is LLVM IR. These are some of the many languages that are supported, also some of the many platforms that are supported. So if we look at this, however, if you look at the targets, you notice that that's not exactly what we want, right? Like we don't want to translate into all these different platforms. We want to translate back into user-defined languages. So I don't know how many people here have read decompiled source code, like decompiled JavaScript, et cetera. So as you know, it's an absolute mess. And it does not resemble anything that a human would write, really. So going from an intermediate representation, if we wanted to use LLVM to solve this problem, we'd have to write our own transpilers that take LLVM IR and go back into human-readable language. And since Compass is in part an administrative tool, but it's also an educational tool. It's a lot of people's first experiences with MongoDB. And so we really want to make sure that the code that we generate is easy to understand. Also, how likely are you to use a snippet of code generated by an application that you have no idea what it's doing? Generally, I would never copy and paste anything into my code that I don't either know that I've written myself or I can follow line by line exactly what it does. So in this case, it doesn't look like we can use LLVM IR directly. So you might ask, all right, so we can't use LLVM IR, maybe we can write our own intermediate representation. So this example is a pretty simple Python function. It's just a linear regression. And so what that looks like in Python actually looks something like this in intermediate representation. So, and this is actually more like a third of the generated code for that simple 10-line function. So intermediate representations are very wordy. They retain a lot of information, and it's not actually very simple to just design a new intermediate representation. That's somebody's PhD thesis, maybe somebody's startup idea, not necessarily something I want to do basically as a side effect of a project that I'm already working on. So intermediate representations in general does not seem like we could potentially use that for this problem. So what else can we do? How many people know what Babel is? Great, so I think it's pretty safe to say that the most popular transpiler in the world is Babel. And what it's used for people who haven't used it, is translating between JavaScript versions. So say you want to have lots of support for your application, you need to pick an old version of JavaScript. Nobody wants to write old JavaScript, you want to use all these new fancy features. You write in the new version, and then that gets transpiled into a more compatible version. So this is how Babel works. Problem with Babel is that it just parses JavaScript. Lots of different JavaScripts, but that doesn't solve our problem of supporting Python, C#, etc. So what do we need? The thing that we can pose the question, the way we can pose the question is to say, we don't actually need this magical transpiler that goes from everything to everything at one time. What we really need is more like a configurable transpiler. So what we need is something where we can have a translation technology that we tell, I want Python and I want C#, or I want some combination of languages. And so you can configure the transpiler so that it will support all these different options. Something like that. So to take a quick break from implementation details and talk a little bit more formally. So the way that we want to define our technical problem is, firstly, we need to make sure that we only do the work one time per language. What this means is that if I am writing support for adding Rust, that I want to add support for Rust as an input language one time, even if there are 10, 20, 30 different output languages, I only do the work one time. This also means that I add the work for Rust. I don't have to separately add work Rust to C#, Rust to C, Rust, etc. So the second half, and that can be formalized into we want to solve the problem with a linear development time as opposed to a quadratic development time. The second half of these technical specifications would be we want to ensure that you can write your input language without being an expert in any other language. So if you're adding support for C#, you don't need to know the implementation details of Java, Rust, or any existing language. We only care about the language that we're adding. And this is my terrible diagram for that. The idea is that we can live happily isolated in the area that we're contributing to, and we don't have to worry about what somebody is doing, maybe concurrently, maybe in the future, maybe in the past. It shouldn't matter. So this also applies for target languages. Talking about input language, talking about output language, doesn't matter. So the MongoDB community is huge. And the great thing about open source in general is that there are huge communities with official support and conferences for the language, but then there are also pretty tiny, often very passionate communities, like for example Rust, although these days the Rust community is a lot bigger, that MongoDB as a company probably doesn't have time to write drivers for brand new languages, but we do have a responsibility to make it as easy as humanly possible to write your own. So we not only want to allow you to read our specifications and know how it works from the inside so that you can write it yourself, we also want to make it really simple. So that also ties into my next point, which is at least I am a remote employee. So I work in Sweden. The headquarters of MongoDB is in New York. My manager's in Berlin. A lot of my colleagues are in Berlin. And I also have a lot of colleagues in Sydney. So we're pretty much all over the world. And that means that we work in many different time zones. And also if I'm dependent on somebody to review my code, that could mean a 24-hour delay. It could mean a 48-hour delay. If it's on a Thursday, I might not hear until Monday. So we wanted to develop this platform, or we wanted to develop this product in a way that made it possible for people to do async development. And I don't just mean relying on GitHub, relying on version control. We really wanted to do the simplest, easiest thing, which is have people write totally discreetly. So if you're over there developing Java support, I can be over here developing Rust support. I don't need to know anything about you, and I'm not reliant on you to get my code into the database, or sorry, into the code source. The other part of that is that the people who are maybe super passionate about MongoDB, super passionate about their language community, also potentially compiler experts, that seems like that Venn diagram is maybe not huge. So something else that needed to happen for this project is we needed to ensure that people could contribute and get the bottom line, which is exporting their queries and aggregations in their preferred language without really being compiler experts. So if, as an open source company, we say, oh yeah, we really want you to contribute, please contribute, we really appreciate it, it doesn't mean anything if it's not actually doable. If it's, yeah, we're open source, but in order to contribute, you need to have like 15 years databases experience, also, you know, a computer science degree, a compiler's course, that kind of thing. That's not really that's not really truly open to everyone. And so in order to really encourage contribution, we wanted to lower the barrier to entry. So how do we do that? So I'm going to summarize the requirements that I've said so far in the talk. First thing, we need to accept an arbitrary number of input languages. So that was our language modes. Arbitrary number of output languages, that's export to language. We want to support distributed development. We need a linear time development cost, so we don't want to write n squared numbers of compilers. And then I may not have mentioned that Compass is an Electron app, which means that we needed to write it in web-friendly JavaScript, which means that everything has to be basically in pure JavaScript. So I know I've gone pretty fast, but are there any questions so far before I jump into the solution? Or is it clear? Great. Cool. So now I've...
Just a question about semantics. Are there to be retained, obviously, but about the languages don't completely overlap. So how do you deal with that problem?
Sure. So because this transpiler in its current form is for transpiling MongoDB queries and aggregations, it by definition has to have equivalencies in every language because it's a query language. So if you use MongoDB in JavaScript, you have to be able to represent your query identically to C# because it's a query language for a database. So if we were to expand it into higher order language things like classes, then we would sort of reach more ambiguity. We would reach things where there isn't an obvious translation between languages, but because right now, truly we're translating between semantics, we're not translating between concepts, we're guaranteed that we can always do a one-to-one translation. But I'll talk a little bit at the end, especially if there's more time, about when we do expand it to things that are more complicated than just a query language, how do we approach that? Sorry, a little bit of a cold, so I'm sorry if my voice is scratchy. Okay, so how do we solve this problem? In order to explain this problem to you, I have to do a little bit of compiler 101. So this is sort of classic concepts that apply to pretty much every compiler that you've used. So these are the stages that a compiler would generally go through. So this illustration was done by my colleague, Irina. She's done a bunch of illustrations for this talk. If you see an illustration going forward and it is beautiful, it is done by Irina. If it is ugly, then it's done by me. So case in point, this is one of mine. First thing, the first stage in translation is to build a tree. So you take your input, which is a string, and you put it into a database, basically. So what this is a object literal, so we're talking about a very simple code snippet in which we just have a document. In order to build a tree, what that would look like is we have an object node, we have our key and value. In this case, we have a key called today, and we have a value called date. And you can see that it's defined recursively with each piece of the input code. So our value of our key-value pair is itself a function. And that is itself a tree, which contains the name of the function and the arguments that are included. So in this case, we don't have any arguments, so that's the end of our tree. So this is the stage I'm talking about. This stage of translating from string into tree is also called parsing. Sorry. Number one thing to know about parsers, they're hard. And generally, if you are given the option to not write a parser, I highly recommend you take it. So also, in order to write a parser, you have to be an expert in the language that you're parsing. And I can't possibly be a language expert in every language that people use MongoDB with. So instead, I'm going to use Antler. So Antler is a parser generator. So it is a tool in which you give it a grammar, which is a language specification, and it generates a parser. What this does is that it allows us to make trees based on input languages. And one of the great things about Antler is that it's open source and very popular, which means that people have written grammars for pretty much every language under the sun. So just like that, I get for free my parsing stage. It also generates a visitor. So this is something I'll explain in a second, but basically this first stage of compilation, I've totally gotten for free from Antler. But the next stage, code generation, I have to do some more work. So what is a visitor? So a visitor is basically a way to visit a tree. So it's a way to traverse a tree. The details of how a visitor is implemented, you do not have to worry about. The only thing you have to think about is the way that a visitor visits nodes on a tree is that it has a set of methods. Each method is specific to the type of node. So if I have a string node, it will call a visit string method on the visitor. And then it will do a depth-first search, calling the correct method for each node that it encounters on its search. So for an example, if I want to translate from JavaScript to Java, so in this example, I'm just going to go from A to B, and I'm just translating a string, which is a very simple case, but it will extend to pretty much everything that you could possibly translate. So for people who have good vision, you can see that the difference between JavaScript and Java is quotes, exactly. So we have single quotes versus double quotes. So the way we go through these stages, first thing we do, we use Antler and we get a tree. And we love this because it's easy. We then apply our visitor. So what the visitor does is it calls this visit string method. I, as the developer, come in at this point and I write the visit string method. I know how to translate my visit string method because I can extract the value of the node, and since I know I'm translating into Java, I just add double quotes on either side. Obviously, in the actual application, I have to think about things like escaping different characters, but for this example, I'll just keep it super simple, just swap out the quotations. So there, we've done a simple translation from A to B using Antler and a visitor. So what does Antler actually look like? So say I have a slightly more complex expression. You can see in pink, say I'm doing something like 1 plus 2. Oops, let me show you what that actually looks like. So what I'm going to do here is use this IntelliJ Antler plugin, which I highly recommend anyone who uses Antler to use, because it allows you to build parse trees and see them built as you type. Excuse me. So for this, this is the ECMAScript grammar. So this is the language specification for JavaScript. And here I can write my expression. Is that large enough? I can make that way bigger. So that's my input expression. And then here I have my tree. So what you see here is that you have your additive expression, you have a left side, you have your operator in the middle, and then you have your right side. So this pretty much resembles what we would expect. Say I want to do it in a different language, also using ANTLR. So here I have the Python grammar file, and here I can do the same thing. And I can have my input expression, and then I can see the tree being built on the other side. So here we sort of see this, we have the same structure. We have an arithmetic expression, we have a left side, an operator, and a right side. But you can see immediately between these two trees that while the bottom line is the same, the actual implementation details differ. So there are a different number of nodes, different number of children. Basically, the names are also different. So we have additive expression here while we have arith expr. So the reason that these two things differ is because what ANTLR generates is actually called a parse tree. So parse trees, go back. So parse trees are trees, they're data structures for your input that include all of the information original to the code that you first input. What most compilers use is something called an abstract syntax tree, which is basically an abstracted, optimized parse tree. The thing about ANTLR is that ANTLR generates parse trees, not abstract syntax trees, and it's also immutable. So I can't translate my parse tree into an AST without going through a lot of pain. So what Babel does, and what a lot of transpilers do, is they translate the input code into an AST, which functions basically like an intermediate representation. But we can't do that, because we don't have an AST, and we don't have the ability to create an AST. So what we're doing in this transpiler is we're going input, parse tree, directly to language translation / code generation. So how do we actually do that? What does that look like in code? So as I mentioned, ANTLR gives us a sample or generated visitor class. What this does is it generates a class that is a series of functions for each type of node that is basically empty. All it does is it recurs on the child. So if I want to implement a visitor, I subclass it and I selectively override the methods that I want to actually do something. Otherwise, it will just continue traversing. So we can't use one visitor for every tree, because as I showed you, the trees have different names and they have different, slightly different structures. So since the way that the visitor pattern works is that it looks at the name of the node and then calls the name of the function, it's actually a very big problem that we have different names for equivalent nodes, like arith expression versus like bin op. So how do we get around this? So in order to actually generate code, we do the same thing for every language. We'll always visit our left child, visit our middle child, then visit our right child, then concatenate them. So in order to support multiple tree formats, what we actually want to do is abstract the heart of the code generation into a superclass, and then have the visitor class act instead like a code generator. It acts a little bit more like a layer of abstraction, where the visitor knows the names of its own nodes, and it knows that it needs to call the superclass method, and that way we can use the same code generation code regardless of what the tree looks like. So what that would look like is, say I have my Python visitor, I have an and expr, and then I have my JavaScript visitor where I have my logical and expression. And then I have my shared superclass that does the actual code generation. Visit my left child, visit my right child, and then concatenate them with a double ampersand. Because in this case, I want to translate into languages like C-style syntax languages like Java, C++, C#, etc. And you can see here that what this is doing is that it's actually accepting the superclass as an argument and then constructing a class that inherits from the superclass that it was passed as an argument. So this is where we get into metaprogramming. So metaprogramming is the process of writing code that generates code, and that code that is generated is what is actually run. So what I'm doing here is I'm generating a class that can then get applied to translate between languages. So you see here that these two methods differ, but they both call this generate and expression. And then I get the result. But the problem with this is that I've now showed you how to accept multiple input languages, but I'm still just generating one output here. So how do I actually make this output differ between languages? Excuse me. So how do we actually solve the problem of translating multiple output languages? So we can apply a very similar trick as we did with the input languages to the output languages. And so since our visitors work now mostly as abstract interfaces, except there are no abstract interfaces in JavaScript, and JavaScript inheritance is very kind of fast and loose, we can pretty much do anything we want, we can fake the idea of an abstract interface in order to allow us to extract the differences between languages. So what this would look like is that we add a new concept called a generator. So generators are basically subclasses where we actually generate code. So we have, say, a generator for Python, which uses the AND keyword, and then we have a generator for JavaScript, which would use the double ampersand syntax. And then in our abstracted shared superclass, we call emit and expression, which is defined in our generator. At the time of compilation, this method isn't defined. But that's okay by us because JavaScript is a dynamic language. It doesn't matter. If I mess up and I forget to define emit and expression, it'll yell at me when I get there. I don't have to worry about it right now. So how do we compose this transpiler? So as I mentioned, we have this empty generated antler visitor class, which is basically just infrastructure for us to build on. Oops. We then have our code generation visitor, which is our abstracted, actual algorithmic translation between language happening. So like control flow happens in this method. We go left child, we go right child, or any combination of those depending on the thing that's getting translated. We then have our input language visitor, which is our abstract interface that allows us to deal with trees that are actually coming in slightly different formats. And lastly, we have our generator, where the actual translation and the generation of code happens. So we define input language visitor by input language. So if I'm going from JavaScript to Java, I would have a JavaScript visitor. And then for my generator, I would have a Java generator. And that's what that actually looks like in code. If you see that the order is reversed, because we're always passing our superclass to our subclasses. Okay, so I mentioned that BSON is basically JSON plus some extra MongoDB specific stuff. So hey, we have all of these classes that MongoDB provides usually via a driver or a BSON package. So how do we tell the difference between those? So I want to translate one code snippet that has a date, one code snippet that has an object ID. We're going again from JavaScript to Java. You can see that the differences here are syntactical, right? So in JavaScript, we have dates. In Java, we have slightly different format of dates. We also care about the new keyword, which is not true for languages like Python, for example. We create our two trees, we do our first step in translation, but now we have a problem. Because right now our trees that we've generated from our input code look identical. And if the trees are identical, we will do identical things because the control of the program is dependent entirely on the visitor. So how do we solve this problem? We need a symbol table. So this is the last slice of sort of general compiler principles. Most compilers use something called a symbol table, which is how we keep track of names. So, seems like I have some time. Symbol tables keep track of names and metadata. So names are things like function variables, class names, etc. So it could be library-defined variables, or it could even be user-defined variables, and they're often scoped. So what do we do when we visit a symbol? So in a tree, I find a symbol node, and my visitor says, I need to look this up in the symbol table in order to get some metadata about it. I look up the symbol, and I decorate the node with the information that I need. This is also where type inference happens. This is where we are able to do type checking. If it's not in the symbol table, we have a problem, we have a reference error, and then we return the name to the parent. So what's actually inside of the symbol table, you don't really have to worry about the specifics of what goes in a symbol table. This slide is just here to show you that it's actually not that much information. It's kind of like, is it a function, is it a variable, does it have arguments, does it have subclass or attributes? But the thing you do have to care about is this field called template. So templates are functions, as is true in all languages, accept strings, generate strings. So templates are functions where we can actually sneak in a significant portion of our translations. So inside of our template, we can have a simple string function that returns the name of the symbol in the target language that we want to translate to. So if I'm visiting a symbol, I can say, oh, I have a symbol, and I know all of this metadata, and I know that in Python, this symbol is called this. And so then I can generate that based on what's inside of the template. Every output language defines their templates in a YAML file, which means that they're now loadable. So I have a symbol table in which I can load these template files in based on the language I'm translating into. And YAML is basically JSON with comments, so it's very simple. So this is what it looks like. This is the symbol file. This is the template file. In the respective time, I'm going to skip the details. But the thing to know, in a similar way to how we have visitors and generators, we can define symbols for the input language and templates for the output language. And what this actually means is that we have our composable transpiler. This is the same slide as we had before. But we can now give the transpiler an instance of a constructed symbol table that is appropriate for our input and output language. That way, the transpiler knows what the thing is called when it looks it up in the template file. So that was a little bit fast at the end there, but the idea is that we get our tree, our first stage, from Antler. We then visit it and abstract the difference between trees and call this shared code that we use for all translations. If we reach a symbol, then we can look it up in the symbol table and we can know what it's called in the library language that we're translating into. So how do you actually contribute? You just write a template file. So template files are lists of functions, and you can think about it like taking a quiz on your favorite language. What do you call an int? What do you call a double? What do you call an object ID? And those are just simple one-to-one translations, and these are these tiny building blocks that together allow you to translate an entire language. So what does that look like? Say, let's talk about longs, because longs are called different things in many different languages. For Python, it's called int64. For Java, it's called long. And for C#, it's called int64. So if you look at these functions, they're really, really simple. And for those of you who aren't familiar with JavaScript template syntax, what the $bracket is just it's passing an argument to the template. So these are the JavaScript language templates that go inside of the Bson transpiler's symbol table translation. We can also expand our templates so that they include literals specific to a language. What this means for us is that we can actually kind of get rid of our generators because we no longer need to do that type of translation for inside of different methods. We can just look it up in the symbol table, which means that basically 100% of the translation happens inside of these template files. So as a contributor, you only write a template file. You do not need to write a generator. That's it. That's how you write a template. Hopefully that's inspired you to add your favorite language to Compass. If you want to add a new input language, you just write a visitor. So that's a slightly more complicated case, but the concept there is just understanding that all languages build parse trees with the same concept. They just might have some naming differences, so you would write the visitor so that it abstracts the differences. And it also includes generated driver syntax. So I have 5 minutes left. I can talk briefly about future features. So we've done all this work, and now we have this any translation to any translation for MongoDB queries and aggregations. What do we actually do with it? So we can generate examples for MongoDB University. MongoDB is crazy about providing really good documentation. We have the university website, which gives you certifications and how to use MongoDB either as an administrator, as a developer, etc. Right now, all of those examples are written in shell syntax. But wouldn't it be great if you could just automatically translate from the shell syntax into your preferred syntax on the web page directly? And you can see side by side how those code samples would differ. This also means that all the information online, the MongoDB JavaScript community is the largest. Most of the Stack Overflow questions are in JavaScript. If you're using a different language, you have now this vast resource of solutions that you can now use in your language without having to translate and worry that they don't apply directly. We can stick it in front of the shell, and we can expand it to support entire languages, which would, as you mentioned, open the door to some more ambiguity. So thanks. I want to thank the other members of the Compass team, and I also want to thank, again, the organizers for having me. And sorry that it was a little fast at the end there, but I am available to answer any questions, either on email or in person. More than anything, I hope that this was exciting for you to hear about. Thanks.
Does anybody have any questions for Anna? We've got, all right, we'll go one there and one there, and we should be able to just make it. Can you make them quick?
Yep. How do you deal with imported dependencies on the input language, if at all?
Import dependencies on the input language?
Yes.
So if you are writing MongoDB queries and aggregations, you can't really import libraries. But if you were to expand it to import libraries in your input language, in theory, you could apply the transpiler to your source, but I think that depending on the language, like if you're using Node, the source is available, but if you're using like a Java binary, that seems like a hard wall that is not really solvable right now.
Who was the other one? I've just forgotten. There we are.
So as I understand it, you're assuming that each language has the same AST structure when it comes to branching nodes. Hypothetically, what if a language had, for example, a different order of operations? I'm looking at you, PHP's ternary operator.
So the way that you would get around that is that you would map from your, say, left associated language into the sort of standard, which at this point is JavaScript. And so the place you would do that is you would do it inside of the visitor. So what you would do is you'd probably do more than one pass, where you would, because you can control you have complete control flow within the visitor, the input language specific visitor that you can then go down, figure out what's going on, reconstruct it, and then visit it again in order to make those changes between languages.
Anna, thank you very much indeed. On behalf of the Linux Conference Gold Coast, please accept this little gift.
Thank you.